Okay, hello everyone. My name is Andrew Reed. I'm the chair of the Materials Science track here at SciPy 2020. This is the Q&A session for that track. Hopefully you have all had an opportunity to view the videos. The talks are all really good. The scheme here is we're going to do the Q&A for each of the talks in the order that they are in the schedule. I should mention also first there is a hashtag Materials Science track channel in the Slack, so that's a good place to share notes and talk about things that we maybe can't cover here. The scheme is we're going to do the talks in order that they are in the schedule, so that's the AIDA talk, then whombeblue, then PyRS, then PyMKS, then the 1000X lab. The C3DP guys from Oak Ridge did not provide a video, and as far as I know are not here, so we will not be hearing from them. Each project will get, or each talk will get 8 or 10 minutes or so. They'll start with a brief summary, and we'll have 10 minutes including the summary for questions, and then we'll have a few minutes at the end for general discussion about materials. So I see there's already a couple of questions, mostly for the AIDA people, so I'll just go ahead and foreground. Simon, you want the slides or?
Yeah, sure.
Okay, so take it away, Simon.
Okay, yeah. I just wanted to before I start, very briefly mention that I'm super thankful that this conference was pulled together so on short notice, so the virtual space. I just think that's really amazing, and I'm really thankful that I could still attend the conference in this way, and that we also get a chance to present our work. So this presentation that we gave is on AIDA, which is a fairly mature software for managing simulation workflows, specifically for the high throughput and high performance space, and with a special attention to automated provenance tracking. And the talk was recorded together with Sebastian, but there were a bunch of people involved in preparing it, including Leopold, who's joining me for the Q&A. And I wanted to, for this summary, I just wanted to very briefly introduce this concept of provenance tracking in the way that we interpret it. So data provenance essentially means data origin. So we're interested in knowing where is data coming from, how was it produced, with what input data. So in the simplest case, you have this kind of calculation where you have a single block that is computing something on some input data and producing some output data. And if we care about reproducibility, where is data coming from? How was it produced? And we need to keep track of this specific relationship. And if you have only, just a few calculations here and there, and just a very small parameter space, then you could probably do this by hand. Although in practice you might fail anyways. But especially when we go to high throughput. So speaking of hundreds, thousands, or even more parameters that we want to explore with high performance codes, then this kind of graph becomes very complicated really quickly. And so I pulled up this illustration from the talk. That is a real provenance graph, so the exact same concept, but we can see that once you enter a real study, that this becomes very quickly untractable. So this is not just a pretty picture, but it's really an illustration of like how necessary it is to think about this problem and to have some kind of systematic approach to solve it. And AIDA is designed to assist us with this. So it's a complete solution for driving computational science and simulations. And for that purpose, it has a workflow engine, so you can define workflows and then execute them. And you can do that either on your laptop or your workstation, but you can also do it on supercomputing clusters. So there's built-in support for standard schedulers like Slurm and Torque and so on. And then what I consider maybe most unique to AIDA is really this data provenance tracking. So every data point can be very well associated with the specific computation that was done to produce it, and then you can query this graph and explore it. And then also we have a plugin system, so it's possible to extend AIDA. So if you want to integrate your own tool, your own code, you can write a plugin, and you can then publish that plugin, and you can do that on GitHub or PyPI. But in addition, you can also register it with the AIDA plugin registry. So you essentially publish it to the AIDA user community, and that's really great because now you can share the work of implementing these workflows and making it all extendable. And I think it's a really nice way to kind of rally the community behind this. And then with AIDA 1.0, which was released last year, there were various performance improvements, and we can talk about those. And that's it.
All right. So I have a number of questions in the question box now.
Should I?
Really often the same person. That's cool.
Screen.
So the one with an upvote is about is it possible to quickly create parameter sweeps?
Yes. So the way it works is that you will define a workflow that you want to run, and into that workflow go certain parameters. So for us, it's typically some kind of structure, some kind of potential or something, or parameters that you want to explore. And so you run those workflows on these input parameters, and they are all going to be run through a scheduling system, and we have so-called daemon processes that are going to orchestrate that process. And so you can run lots and lots of these workflows, again, both either locally if you're pretty lightweight or in a supercomputing cluster.
Yeah, and just to say that in the end, it's just going to be a Python loop. You make a Python loop over the parameter that you want, or parameters, double loops that you want to loop over. You submit your calculations. It's from the Python API, and yeah, loops is definitely something that is very easy to do in AIDA.
So it looks like also there's a group of questions that all kind of, to my mind at least, hover around or gather around the issues of sort of general flexibility. So these are all from NR. So is it possible to add breakpoints? Can you continue a workflow from a place where it left off? Is there a UI for workflow management? And can you stitch workflows together into a pipeline? I think those are all closely enough related they can maybe be answered together.
Okay, I can give it a shot, and maybe then Leopold can help me. So in general, it's possible to continue workflows from specific points. So let's say you have some kind of error state or something like that, then you can recover from this and try to restart it. There is, what was the other question? A lot of questions at once.
So there was a question on whether it's possible to stitch workflows together. This is definitely possible. So one workflow can call another workflow, can call another workflow. You can nest it as deep as you want. There was a question about restarting. Yes, you can. So everything is tracked in a database, and all of these workflows and the outputs of workflows, they are stored as nodes in a what corresponds to this provenance graph. And you can load any node in this provenance graph and use it as input to your next calculation. When you meant breakpoints, I'm not quite sure what exactly this means, but so if you mean points that you can then use to branch off and then maybe start a couple of new workflows, that is definitely possible. But if you have more specific questions, please feel free to ask again or write in the chat.
There's also the one about UI for workflow composition. I wasn't...
Right. This is something that we don't offer at the moment. So AIDA, let's say on the broad map of workflow managers, AIDA has chosen a relatively flexible workflow language that is very close to, in the end, what you can do with Python. So you have essentially the power of Python at your fingertips. If you write an AIDA workflow, you can, in principle, query at each step of the workflow the whole provenance that has been generated up to that point. And so generating a graphical user interface for writing workflows is something that would be quite difficult for a system like AIDA, and is something that we haven't done. What we have done, however, is there is this so-called AIDA Lab platform. I will put a link in the chat later, which is an interface for running workflows that have been implemented with AIDA. So you can make it super simple to run an AIDA workflow and to give an example from our field, so material science, surface science, we have groups that are kind of mixed experimental and computational, where the computationalists essentially maintain this AIDA lab platform and write workflows that can then be used by experimentalists either to analyze data directly from the machine where they're, for example, running that is connected to their scanning tunneling microscope, and also launch calculation workflows themselves. So maybe Simon wants to add a few more words on the AIDA lab, and I put the link in the chat.
Sure. So AIDA lab is in essence just a bunch of Jupyter notebooks, and it's kind of nice because it allows us to provide a more user interface that may be easier, more accessible to experimentalists, for example. So they don't need to, literally write Python code if they don't want to.
Okay.
But with respect to the UI aspect, one thing I wanted to add is there is the option to generate these graphs that I showed earlier very easily. So if you want to debug your workflows and see how they're connected, that's a good way to do that.
Okay. So there's another question of asking about searchability. If someone runs a parameter sweep, how hard is it to go from a result that looks interesting to the data that created it?
So AIDA has support to help you build queries on your provenance graph. But it boils down a little bit to in how well you prepare your data. If you just dump everything into the provenance graph, you will have just as hard a time finding things as if you dumped a bunch of files somewhere without any system. So you can always query for the parameters that you use as inputs. If you want to query with something else, then you might want to do another sweep over that graph and add that as so-called extras, just additional attributes that will be indexed that you can then also search for.
Exactly. So you can use this to kind of annotate your data to make it easier to search. So you can say, that this is something that I'm interested in. So you once do the kind of the graph query that really takes into account how everything has been computed. And then the next time around, you can say, I want the nodes that are tagged in this way.
Cool. Okay. There's another question about how does AIDA compare to other data pipeline frameworks like Airflow? This is in the talk a little bit, right? We had a slide about.
Yeah, so do you want or?
Sure. So as was mentioned in the talk, there are, of course, loads of other workflow managers. So if you go beyond Python, there's hundreds of workflow managers out there. So one of the two kind of key focuses of the design of AIDA has been the plugin system. So making it easy to essentially plug in support for new code. And not only for codes, but we also, so through AIDA, through Python packages, you can distribute plugins for calculations, for workflows, for new data types, etc. So on this AIDA plugin registry, I will put a link as well in the chat. People can register these plugins and share them. And then another key point is the focus on provenance. So there are other workflow managers, even in materials science. You may have heard of, for example, Fireworks and Automate. Yes, from the Materials Cloud project, from the Materials project, and more. So, which have their own design choices. What differentiates AIDA, I think, is this focus on plugins and also building kind of a community to write these plugins. And on the other hand, being really strict about making sure you store all information that is necessary to reproduce your calculations 5 years down the line.
Yeah, I agree. I think the provenance is really one of the most unique features that are hard to find somewhere else.
So that your first part of that answer segues nicely to what will be the last question here, which is, can you mention some of the more popular plugins and what kind of tasks are possible with plugins?
AIDA is originating from the field of materials science in the DFT community. So many of those plugins are centered around that field. So we have a quantum espresso plugin, for example, that is very popular and very well maintained. there are a bunch of others. Maybe Leopold can also mention those. But I will say that in general, the drive for us is really to branch out. So that's why we're in the material science track, but we're trying to reach more users outside of our field and move beyond material science, because AIDA is in principle completely domain agnostic. So it doesn't really matter what specific field you're in. You should be able to use it.
Yeah,
okay.
Just to, sorry, okay.
I think we're actually a little over time already, so I think we need to stop there, and we'll invite the whomd guys up. I'm going to
thank you.
assign you guys to wherever the remove button takes you. Okay, so the whombeblue speaker is Brandon Butler, who has been invited. There we go. Hi, Brandon.
Hello.
Take it away. A brief intro and then Q&A.
Sounds good. So I'll go ahead and share my screen then.
Yep, that seems like a good step.
All right. Can everyone see it? Yep. Seems like
good.
All right. So I presented on whombeblue, which is a high-performance, scalable particle simulation Python library, or Python package, whatever word you prefer. And so I focused primarily on let's see. It is deciding to, of course, have a technical error right now because it's what it's going to do. Let's see if I can't fix that real fast. Nope. All right, so give me 1 second. I'm going to exit out of this and reload it.
Maybe just summarize the main points real quick.
Yeah, I'm sorry. Let me stop sharing the screen because it's not going to help. So the main point was essentially... okay, there we go. Still stay there. So the main point was effectively, why does whombeblue exist? And then also... why are we changing to a new API with version 3, and what does that give us, and how we better integrate with the SciPy community in general? So to give a brief overview of what whombeblue is, once again, it does molecular dynamics and hard particle Monte Carlo simulations, and it does this fast on GPUs. It's designed for GPUs it's optimized for use on GPUs. And with version 3, we try to extend the customizability that we give users into interfacing with this already fast engine.
All right, thanks. So we got one question already. Have you compared it to Taichi.graphics, which I'm not familiar with, which is a single node multi-GPU tool, apparently?
So as far as I'm aware, we don't have any benchmarks with that particular piece of software. We have done benchmarks before, and we are comparable, generally outperforming other engines when it comes to use on GPUs. We support multi-GPU configurations, including using unified memory, and so using multiple GPUs on the same node. We also scale across nodes, so you can run whombeblue on thousands of GPUs. So it's not limited to a single node, which I guess would partially answer that.
Okay. So I had a question, which is, I think, maybe kind of unfair, but since you brought up in the paper and in the talk, you brought up the idea of like scaling and the idea to scale very large. Have you thought at all about fault tolerance? Like, so when, once you're at, I know in the exascale community, there's been some conversations about like, if we have 150,000 nodes, they're not all going to stay up all day. What do we do if something breaks?
So with regard to that, if you're running a simulation and let's say a node crashes on the cloud you're running on or the supercomputer, wherever you're running, the way we do domain decomposition, which is our fundamental way of parallelizing, for those who aren't aware, in MD and MC simulations, a lot of times you will decompose a global box that contains all the particles into multiple smaller boxes, and you then store that data local to a MPI rank or potentially even a node. And so if you do that, then you lose that data. And so you lose the ability to be fault tolerant in that as a consequence of having that scaling. And that's traditionally the way it has been done in molecular dynamics and Monte Carlo simulations. But That's not to say there's not potentially a better way. I don't know if it's just been thought up yet.
So that's my question was actually stolen from the one of the HPC sessions where they talked about that. And so I had that question for the Leggett guy. I think it was Leggett guys, and their answer was they're not doing that. But Leggett is built on top of this thing called Legion, which is, I think, I don't know much about Legion. I'm mostly learning about it from this conference, but it has within it a task graph. And one of the things about task graphs is you can, if you have a failure, you can isolate it, and you know like what's downstream from it in terms of dependencies. So you don't need to rerun everything. You only need to rerun the tasks that depend on the thing that failed. So maybe that's a thing to think about.
So I can
maybe for version 4, that's probably like an architectural overhaul, right?
Yeah, that would be quite a one. I can say this. So we do generally in this community, you generally are storing trajectories intermittently. Given the nature of the computations, you spend most of your time calculating forces used to, in molecular dynamics, I'm talking about molecular dynamics now, to integrate Newton's equations of motion forward. And with that, as long as you are doing fairly regular, which is typical, outputting trajectories, you're not likely to lose much time.
Okay. All right. Thanks, Brandon.
Yep.
I think we'll move on.
Okay.
So the next speaker is Wendu Zhao.
Okay, actually, my talk is a little bit from the other people's because the software PyRS we are developing is for the a neutron user facility of the Department of Energy, and this is targeted for the general user who come to our facility to do the experiment, especially for the engineering material experiment. So the name called PyRS is because Pi is for Python, RS is for residual stress, and the beamline is particularly designed for that type of experiment. So what actually we want to present is that is how our user facility to build a software for general users, starting from collecting all the requirements and think of how to do the rigorous engineering by using CI/CD and writing full list of user documentation. And eventually we start to build with the software with the backend and with composed of all the algorithms, and the front end, basically they are the friendly user interface. And on the other hand, the challenge is mostly because of we don't have users, except the instrument scientists who work in the lab. The general users who come for the experiment, they may only use the software once or twice in their life, and they only have very short time to learn how to use it. So it's more like how to design the software, be more intuitive to use and very robust, because the one is the code cannot be crashed during the using. On the other side, the result must be correct or they affected the paper they wrote. On the other hand, the another challenge is that the performance, because the user working on the code, the software to reduce their data and visualize their data interactively, and so the user experience is very important. Hello?
Sorry, I was muted. All right, thanks. So your video is frozen for me. I don't know if it is frozen for others.
I thought it even frozen for myself, so I don't know.
Okay. Well,
whether
hopefully
you can hear me or not.
Yeah, I can hear you. That's possibly enough for now.
Yeah.
So I agree with your priority of making the software easy to use.
Yeah.
One of the frustrations that we've had with actually a Crowdcast is an example of this. I was beefing about this earlier in the session, where complicated things that you need to do infrequently are very challenging for in technology. That you have to find the interface, and it's important to get it right. And if it's infrequent, it sometimes is also high stakes. So that's an important priority, and it's nice to see that being addressed. I did have a question. Again, this is I feel sometimes like my questions might be a little unfair, but anyways, the thing I was thinking about when I was looking at your talk was I was curious whether the software is as instrument specific as it sounds. Is there any possibility that someone could come to the instrument, collect data, and take the data off-site back to their institution and reduce it there in a less time-critical manner, or is the workflow really where the data reduction has to happen on-site because of the data volume or the availability of resources or whatever?
Basically, the data volume can be very huge. On the other hand, the expectation from the DOE to us is the user comes to our facility for experiment, and they will leave with the reduced data they can use directly for analysis. So the software actually will can be, for example, if you have a Linux box and you use online installation, you can just bring the data back to your own facility and do the result. Yes, no problem.
So what are typical data volumes? Are they tens of terabytes or a few gigabytes?
Actually, is gigabytes.
Okay.
Yeah, or several 10 gigabytes at most. Because we only, in our neutron facility, we only record each neutron event, and the neutron is very expensive to generate.
Aha.
And usually, typical experiment maybe 10 to 12 hours.
Okay, interesting. Were you? Is there legacy? So many years ago, I was peripherally involved, actually, with the engineering diffraction in the dance project. Is there any benefit? Have you gotten any benefit from that? Have you heard of that?
You were in dance project, and maybe we meet with each other because I was a postdoc in the dance project. For the
possibly.
Back to 2016 to 2019.
Yeah. It was longer ago than that, but well, this is tangential now, but I have a finite element tool that was a candidate for the engineering diffraction model. We were eventually not included for other very good reasons, but
yeah. So basically, that's the same. On the other hand, this software is especially designed for the one in Haifa in the reactor. I think a dance project is targeted for Vulcan.
Yeah, it was the spallation neutron source, I think they were going to. Yeah. All right, cool. Well, thank you very much.
Welcome. Yeah.
We'll bring up the next speaker, which is Berke Yücel from PyMKS. Hi, Berke.
Hi, Andrew. How are you doing?
Not too bad.
Yeah.
So a brief summary of your talk and then some Q&A.
Sure, of course. Let me share my screen. Okay, share screen, this one right there. Okay. Can you guys see my screen?
Yep.
Okay, I'll just quickly go over. So the PyMKS stands for Python-based Materials Knowledge System. We've been developing with this package, Python package, with a sponsor from NIST. Actually, the Daniel Wheeler is our a software guy, so he's been helping us a lot with the development of the PyMKS. So PyMKS is a materials informatics tool. And basically, the materials informatics, I use an example of the bioinformatics because it's a more well-known example compared to materials informatics. So can you guys hear me? I lost the voice.
I can hear you.
Okay.
Because I was muted.
Okay. All right. Okay.
Sorry about that.
It was because of that, I guess. Okay.
It's lonely on the stage here.
Yeah. All right. So basically, the materials informatics is like a bioinformatics. We're trying to understand the hierarchical structure of the materials to basically support the material development and have a better materials. So to do that, we need to understand like how the processing conditions affect the structure, structure conditions, structures affect the property of interest, basically. So the PyMKS basically is a tool that provides feature engineering to kind of understand the microstructure better. Yeah, like actually in a better way. It's a kind of like provide the statistical representation of microstructures to enables us to build this structure to property or process the structure linkages. So it does that through the 2-point special correlations. I explained that in a talk, and basically we have a lot of notebooks in the PyMKS repository that explains the 2-point correlation, how they work. And moving forward, so we address two different types of problems in the PyMKS. One is homogenization problem, the other one is a localization problem. Like a simple example to homogenization is, for example, like from smaller line scale, given that the microstructure image, like it's ACM or TEM, it can be simulation as well. We can try to try to predict the bulk property, might be yield strength, UTS, or thermal property, any property of interest. Localization is like a reverse side. Basically, in a bulk component, if you apply some condition, for example, strain fields, like you try to understand the local points of the strain in the microstructure. So it's the kind of example that I gave in the talk, but like we have multiple notebooks in the PyMKS repository and pymks.org that walks you through the both homogenization and localization homogenization cycles. So with the new version, actually we're releasing the new version of the PyMKS. We implemented task workflows as well, because so when we have a simulation data set, so they are quite large usually, and we have a memory issues. I mean, usually we don't have that issue because we have access to supercomputers, but we want the common user to be able to process big data as well. So we implemented the Dask workflows, and like Dask provides amazing features. Like it's like super simple to use and like other stuff. And basically I walk over like something really simple example. So we're working on a bigger benchmark analysis, basically like the parallelization like across the nodes as well. But this is a kind of like the example that I use for like a single computer. Overall, we can kind of perform the structure to property linkages using PyMKS. This is like a general kind of overview of PyMKS.
Oh, great. Thank you.
Sure.
So we have one question so far. Sure. Simon Adolf wants to know if it's possible to easily integrate your own structure descriptors like SOAP.
Yes, that's totally doable, because like so PyMKS basically like will integrate it with the scikit-learn packages. Like actually we are using the pipelines. I mean, if you have like your own microstructure representation, you can like use it alongside with the 2-point statistics, or like, I mean, it's up to user. So it's highly modular for users basically.
Cool. Thank you.
Sure.
So I have a question. So
sure.
I know I know more about, I think, the older MKS than the PyMKS,
yep. Mm-hmm.
But I know that one of the goals was to eventually have make like the microstructure descriptors available to people, so they don't have to do their own fitting, right? So if I have a microstructure, I can get my 2-point correlations or my descriptors, and then put them in an engine and get like faster results than FEM. Have you thought about that? Have you got to the point where you can export models for people to use?
That's actually something that we're trying to use. Like actually we're trying to build this like a big database of like these models and everything. People just like use their microstructure descriptors and get the prediction out of it. So actually we're working with the like again with the like a nest with the different, I mean Zach is kind of the, I'm not sure if you know the Zach, but we're working with the Zach built this architecture like so that like people can only use the microstructure descriptors and get the like results without using any APM like software or tool.
All right, thank you.
Sure.
I got a phone ringing here, so I'm sorry about that.
That's okay.
So there's another question in the question box. Do you anticipate industry using this to predict, for example, regions in part of a forging where a flaw might happen?
once the international should predict, for example, a region part of the forging where flowing. I mean, that is that's the main goal. I mean, we want we wanted to generate this tool like open source, so that industry and other people. I mean, actually, we know that the national labs are using, a lot of people are using to do something similar to that. But I never thought about specifically for the forging case.
Seems you would need to know the microstructure, right?
Exactly, that is true. That is true.
So it's not obvious. I mean, if the forging people can know the microstructure, they can do a lot of things, including the PyMCast thing.
Yeah, that's true. That's right.
There's another question about is PyMCast restricted to elastic properties, or can it be extended to viscoelastic properties?
So currently, the examples that we have is mostly related to the elastic properties. But I think, as long as you have the microstructure information, it can be extended to viscoelastic properties as well.
Also plasticity, right? I know that.
Yeah, of course.
Surya,
Surya,
I don't know if you have done that, but Surya has done that.
Surya, it's very mainly actual plasticity group. So we're doing indentation and everything. Yeah.
All right, cool. Thank you. So if there are no more questions, we'll move on to the next.
Thank you, Andrew.
Thanks. So the next one is the 1000X lab, and that's Mike Heber. Who has now been invited.
Hello, everybody.
Hey, Mike.
Thanks for coming. So I'll jump through this real quick, a couple of main points, and then we can get into questions. So this talk is a little different. We're talking about here, in addition to software, hardware. So I'm a polymer scientist, and I had a mixed background in simulation and experimental science. And it's kind of fun to be working at kind of this interface, but we're trying to think, what does a future laboratory look like that can generate a lot more data and to be able to allow us to do machine learning and various more advanced computational techniques with experimental data. And our reference point is always what is a typical state of an experimental laboratory, which is in most cases one in which people have to carry samples around and take measurements one by one. And many places you're still writing things down in a laboratory notebook or saving data onto a USB drive. And this is kind of the state of the art, not the edge, but the reality of how, especially in industry, this is the majority of how it works. And so we're trying to think about ways to move beyond that. And one way you could think about doing this is just have a robotic-centric system where you have a very fancy robot that does all the same things that a human does. We need a pretty good robot to do that. So we're thinking of an alternative way where you have what we call digital-centric R&D system, where all the steps are miniaturized, and you have a centralized computer system or network of computers controlling the system, making requests for measurements, getting your data back, and then moving things all along this workflow in an automated fashion. We're not the first to ever think of this idea, but I think one of the differences in how we're approaching this problem is we're trying to build out really low-cost automation capabilities that would slot into here in this material screening workflow, somewhere in between computational screening and then maybe the final, more rigorous experimental validation that you need to do. So any really fancy experiments that are really challenging to automate or just really expensive to scale, you'd still have them in your workflow. But before you get to that stage, what can we build into a system that allows us to much more rapidly filter out candidate materials? So some of the key needs to making this happen that we think is there needs to be increased modularity of different measurement tools, and they need to be built for digital interfaces, right? Not for humans, but for computers to use. And to lower the entry barrier to get involved in this, we need lower cost instrumentation that can lower the risk. And our focus is really on getting this into actual industrial labs. We're not trying to do like sort of hobbyist or very fundamental academic problems. Those are great for proof of concept, but how do we push those ideas into real laboratories that industries around the world are using to generate the products that we consume every day? And so we'd like to get people involved, a broader community involved in this. And we're definitely not the first or the only ones working in this space. But we see an opportunity here when you look at some of the really cool open source hardware. I'm going to jump ahead a little bit for this last one. Some people are designing some really cool pieces of hardware that's really low cost and really easy to make. And it's built to be motorized. It's built to be controlled by a computer. It's not human centric. And so with this idea in mind, we've started this thing called the 1000X Lab, which is an effort to build a community around these ideas. And it's really, again, focused on industry application of these methodologies to materials development. So in February in Austin, we hosted this event, the first Congress for this initiative. We brought leaders together to discuss it, and it's challenging, right? It's hard to get people to understand what this new paradigm would look like, and people are resistant to change because there's certain workflows that have been working for many years, and companies are making money doing it this way. And so it's important to get a lot of people involved and to be heard and to really consider the whole problem and pick away at some of the low-hanging fruits. We had a bunch of speakers. I'm going to skip ahead a little bit. A project that we did that I was involved with at MTHA was we built this automated optical microscope, home build setup, which is a really fun project. And this microscope costs around $1,300 in parts to build it, which is much, much less expensive than a full, state-of-the-art optical microscope that you'd find in many industrial labs today. And I'm happy to answer more questions about that particular project. But this is kind of the thing we're trying to build out. And the question is, how does SciPy people get involved? Obviously, I talked a bit about hardware, but with every piece that I've shown, there's software involved. There's instrument control software, there's data acquisition, there's data analysis and data management tools. And we're looking for, how do we bring all of these things together? How do we find the leading competitor or the leading tools out there to emerge and use them and make them become more standardized in this ecosystem? Like we've seen arise with SciPy, you have a lot of very standard Python packages that everybody uses because they work, and you don't have to reinvent the wheel every time. So this is what we're trying to do with this initiative, and we look forward to you guys engaging with us now and then also in the future when we're able to have future events for the initiative. I'm posting a link in the chat, which has a blog article we recently published that provides more information about the effort, and I'm happy to answer questions about it.
All right, we got a few questions. In order of upvotes, the first one is it's tagged as a mean question. So the microscope parts cost $1,300, but the cost of the instrument also includes 6 weeks of 2.5 engineers doing stuff. How well does that production model scale?
So obviously the engineering time is expensive, definitely. And so you need to be careful about when it's appropriate to apply that time. But now that we've built this microscope, reproducing it's easy. We've built 3 or 4 of them. So the design of it takes time to do the hardware design, to make sure it works, calibrate it, write the software. But it's done now. And so we can easily scale it. And so obviously, if you're talking about overall, should I undergo this kind of project as a consumer, you need to be careful. Is it worth that engineering time to be done? But we definitely, like with our industrial clients, we work with them to help them make that decision and make smart choices about, at the end of the day, they're trying to make money, right? So we need to be cautious of applying the right technologies. And eventually, there's going to be a lot of different tools out there in this ecosystem. And so you won't need to be reinventing them every time. You'll just maybe tweak it a little bit for your particular problem.
Yeah, I guess there's also a potential kind of first mover problem, right? So I guess this is tangential, but if the designs are shared, then somebody has to make the sacrifice, right, to invest in the design, and then other people will benefit from it, which in a competitive environment might be a challenge.
I mean, we already see open hardware designs that I showed. These are mostly by academics.
Yeah, okay.
But there's even companies out there now developing open source hardware and selling it. Because industry companies, they want the support and the infrastructure of a vendor. So who's going to ship it to me, who's going to answer questions if it breaks, who's going to iterate on that design and tell me when there's an update to give me. So there's even an opportunity for businesses to be built on top of open source. So that's the same in software, right? There's companies on top of open source Python packages as well.
So that's a magnificent segue into Blaze's question, which is at the top vote here, which is he says, actually sharing and iterating on open source hardware is hard. Do you have ideas for how to collaborate on hardware? So you were already talking about that. Can you? Yeah,
it's hard because it's not virtual, right? You have to have the actual piece of equipment. So it depends what it is. If it's something that's 3D printed, it's easier. It's not as easy as software, but given how cheap 3D printers are, you can replicate many of these pieces. In some cases, you can't. It's going to be a whole spectrum. There may be central locations where these hardwares are built in some demonstrator lab somewhere that people can come and play with them. I don't know. It's all new, really. It's a whole new experience. There are differences from software for sure, and it's harder. But there's also commonalities.
Yeah, and the roadmap is already, the road is already partly paved.
Yeah.
So we got several more questions. There was a question about how did the DIY microscope speed up the client's process so much more than their previous process, the 25x? This is the example from the talk.
Yeah, so in the previous process, the clients were putting their samples in a standard optical microscope in the lab, and then focusing and taking the images manually. And then you'd load that image up into the Microsoft software, annotate it, measuring sizes of features and lengths and whatever your process is for the features on your wafer, and then recording that data into either on their spreadsheet or somewhere. And so that was their process. And so
automation was
we automated not just like taking an image, it would autofocus, it'll move around the sample and take images. And then the image analysis part is also automated. So pulling out feature sizes and things that they care about. So all of that was completely automated. They still had to physically place the wafer in the microscope. We didn't automate that step yet, but that's the next stage. You could make a whole rack of wafers and just let it run overnight, and it would pop them in and out and measure them. That's something that we're going to be probably tackling in the next phase.
Cool. So there's another question. Do you think this will largely be driven by academia or industry?
Really, we need both. And you can add government too. For example, the NIST people and other national labs are also, I think, interested in these kinds of things. But it's going to be interesting to see. Currently, it's very academic driven, but what we find is a lot of industry people are very oblivious to what's going on in the academy and even in the national laboratories. It seems far away from what they're doing. And part of it's they're not paying attention, but it's just there's a disconnect. Hopefully both. Everyone has things to contribute. Hopefully we can have a community that everybody's involved. That's why we tried to bring together this highly mixed group when we had the first Congress, to make sure that people were feeling like they could say things. There's things we need from every community.
Okay. So I got another question. In the talk, you mentioned the problem of researchers maybe getting data off the machine on a USB stick, and then you jumped to full automation for your sort of goal state. Yeah. Can you comment on the progress in closing the gap between accessibility and measurement data?
So in this particular example, the client was very apprehensive to totally change everything, right? It's a big thing to ask. They're making their business on doing it in a certain way. And so that's part of the challenge of demonstrating a different way of doing it. And you have to start small. So we started with this microscope, which was just slotting into their existing workflow. It's not a fully digital centric workflow right now, but we're trying to demonstrate a small piece of that can demonstrate that vision for them, and get them to expand it out. There may be certain processes that it's just really expensive to automate, and maybe those are still done manually. But it's about continually eating away at that and taking small bites and demonstrating value every step along the way to get there. The USB stick problem itself, you can tackle in different ways. There's ways you can have we've done things where we have file watchers on a computer that'll automatically detect when a measurement file is done and it'll load it to a database. Like for that particular problem, there's solutions there. But yeah, you guys keep working at it and finding ways to add value to the business.
Right. Thank you. So there's another last question. Have you thought about automating more complex imaging systems like an SEM?
It's a lot more expensive to do that. So we're not going to build our own SEM. So there's a place for highly skilled, highly expert instrument vendors. I mean, even in not SEMs, like other instruments, like there may be certain cases where certain types of optical imaging, if you're doing, maybe you're doing 2-photon or something really complicated where the optics has to be just right, you won't build that yourself. But you need to decide what's appropriate for your problem. Like what's the information you really need to make a research decision, and choose accordingly. It would be really nice if more commercial vendors provided better APIs and access to what the instrument's doing. A lot of them are really bad. I mean, they're just bad because they want to lock you into using the instrument software, which is made to work a certain way.
Yeah.
And if you want to get under the hood to do it, to control the instrument and everything, I think it'll change, but only once they have to change it, because it's a long ways away from. There are exceptions. Some companies are really forward thinking on this, but it's challenging.
All right, thanks. So there's something I saw in the chat, which has now scrolled away, and so I can't necessarily credit the person who mentioned it, but it had to do with standards for data interchange between these instruments. So that's something I was thinking about when I was listening to your talk, is that it sounded like there might be a lot of kind of bespoke instruments that, if people, different academic labs have different, they're going to build a thing that solves their precise problem as cheaply as they can. And so it's kind of optimized in a way that might make it hard to generalize or hard to reproduce or inapplicable to somebody else's problem. But if you have good data interchange standards, maybe that could still be part of a bigger solution.
Yeah, I mean, it's like with any system that's built on components. You need to, whether it's forced by a forced standard or whether it's just a naturally emerging best practice that gets adopted, you're going to need that because you need compatibility between different pieces. We're definitely not in the place to be mandating anything, and we don't want to be. So I think our thinking on this is build this community that can decide sort of mutually what's best for this problem. And we're kind of focused in the materials and chemical space. And right now we're largely focused on soft materials because they're easy to work with, or easier as far as like cost for fabricating and measuring and things. But we'll see how things evolve. But we'd like to see at least a discussion start of what should that interface look like and what should the standards be. There already are some probably out there. Maybe some of them are already perfectly appropriate, and then the community can just adopt them as needed.
All right. So there's one more question just popped up in the question box. Is the 1000X microscope hardware open sourced, and where can we get the design files? It is
not currently open source, but we are probably going to do it. I can't say for sure. We're still thinking. The challenge with this is it takes manpower to make something open source, right? I mean, you can build it, it works, but to get it cleaned up and documented well for the external user, it takes more time. And so we'd like to do it, I think, but we'll see when we can get around to making that happen. If the 1000X lab initiative grows and there's more of a community being built there, I think that'll make it easier for us to justify putting in that effort to open source that instrument.
Yeah.
But I'm happy to talk generally about. I don't want to hide any secrets about what we did there. So if you have questions, I'm happy to answer.
So there's somebody in the chat said National Instruments is working on Python APIs for. I think it says NI. I'm assuming it's National Instruments, the labs you guys. So that maybe is a starting point.
Yeah.
So we got 5 more minutes if we want them for general discussion. If anybody wants to shout it in the chat or ask a question, or it's 6 o'clock on Friday where I am, so I don't want to discourage anybody. Don't get me wrong. Someone's posting from where it's midnight. So. All right. Well, I guess that's it. Thanks, everyone, for participating. They were good talks. It was a good session. I hope we got a bunch of questions answered. There is the hashtag Materials Science track channel in the Slack. All this vocabulary. So if people want to continue the discussions there, that's the place to do it. Or I think contact information is generally available. Thanks again. I guess it's 5 o'clock Central Time. There's a bunch of breakout sessions. So, meeting adjourned. Thank you all.
Bye, everybody.